Hi everyone, welcome to Cloud Computing series. Today we'll start from innovative applications. See, innovative applications refers to new and advanced ways of using a technology to solve a problems or improve efficiency in a various fields. Yes, these applications push the boundaries of what computers can do and often requiring a high performance computing and high throughput computing systems. See, transparency in high performance computing and high throughput computing system. Here, transparency means making a complex processes appear simple and seamless to users. Yes, next point is, see, in high performance computing and high throughput computing, we want to make things easy to see and manage. This means being able to access data easily and use resources efficiently, know where processes are running, then manage multiple tasks at once, then make copies of jobs if needed, and recover from failures without much trouble. Yes, next is, see, this table highlights a few key applications that have driven the development of parallel and distributed systems over the years. Yes, key applications domains are science, engineering, business, education, healthcare or traffic control, then internet and web services, military and government applications. Yes. See, for example, science and engineering for complex simulations, then business and finance for transaction processing, and then healthcare for managing patient data and analysis, then traffic control for managing traffic flow and safety, then government and military for secure and reliable data processing. Yes, moving to the next point. See, application demands. See, application need to be cost effective and then collect and process huge amounts of data, then run reliably and scale up easily as more users or data are added. The next is distributed transaction processing. See, widely used in a banking and a finance industry. So banks and financial institutions use these systems to handle transactions across multiple locations. See, represents 90% of the market for reliable banking systems. That means almost all modern banking systems depend on these methods to keep transactions accurate and then reliable. See, banks need to coordinate data from many servers and make sure all copies of transaction records are accurate and consistent. The next is some of the challenges. Lack of software support or network saturation and security threats. There are not always enough tools and software to manage these complex systems efficiently. Network saturation means the system can get overloaded with the data traffic. Then security threats are a big risk because financial data needs to be protected from hackers and breaches. Yes, next is the trend toward utility computing. See, utility computing is a model where customers pay for computing resources like a storage or a processing power or a software provided by a service provider or a similar to how we pay for utilities like electricity or a water. Yes. See, this figure identifies the major computing paradigms, facilitate the study of distributed systems and their application. Means different computing methods help us to understand and develop distributed systems and their real world uses. See, these paradigms share some common characteristics. Those are, the first one is they are ubiquitous in daily life. Means these technologies are everywhere and are a part of everyday activities. For example, cloud services like a Google Drive or a iCloud are used daily. Then the next characteristic is reliability and scalability are major design objectives. That means the goal is to make systems that work well without failing and can handle more users or data as needed. Then the next point is they aim at automatic operation that can be self-organized to support a dynamic discovery. Means the system should be self-managing, self-adjusting and able to discover resources on its own. For example, auto-scaling in a cloud computing where more servers are added when demand increases. They are composable with the quality of service and service level agreements. That means the system should meet quality standards and follow agreed upon performance rules. For example, an internet provider promising 99.9% uptime. The next point is, utility computing focuses on a business model where customers receive computing resources from a paid service provider. It's like paying for electricity. You pay only for the computing power or a storage you use. Yes. For example, Amazon Web Services charges based on how much you use. The next point is, all a grid or a cloud platforms are regarded as a utility service providers. Next point is, cloud computing offers a broader concept than utility computing. Means cloud computing includes not just utility services but also storage, software and platforms. Next point is, distributed cloud applications run on any available servers in some edge networks. These apps don't just run on central servers but can operate on a smaller local servers closer to users. For example, content delivery networks, that is CDNs, that serve videos from local servers. The major technological challenges include a network efficient processors, that is making a processors faster and more efficient in handling a network data. Next is scalable memory and storage schemes. Developing ways to increase a memory and storage capacity as needed without slowing down. The next is distributed operating systems and a middleware for machine virtualization. Means building operating systems and a middleware that support virtual machines running on multiple servers. The next is new programming models. Means creating a new ways to write a code that work better with the distributed systems. Effective resource management means ensuring that computing resources like a CPU and memory are used efficiently. The next is application program development. Developing a software that works well on a distributed and cloud systems. And lastly, exploring a massive parallelism at all processing levels. Means making systems that can do many tasks at once without slowing down. Then moving to the next topic, that is the hype cycle of new technologies. Any new and emerging computing and information technology may go through a hype cycle as illustrated in the figure. Means when a new technologies come out, they usually follow a pattern of excitement and a reality checks. Next is the hype cycle shows the expectations for technology at 5 different stages. Those are, the first stage is trigger period, second one is peak of inflated expectations, then third one is value of a disillusionment, then fourth one is slope of enlightenment, and lastly plateau of productivity. First stage is trigger period. In this, a new technology is discovered and people start getting excited about its potential. Next stage is peak of inflated expectations. In this stage, everyone gets overly optimistic, expecting the technology to solve everything. There is a lot of hype and unrealistic expectations. In third stage, disappointment sets in when the technology doesn't meet high expectations. People realize it's not as amazing as they thought. Then in fourth stage, gradually people learn how to use the technology correctly and understand its real value. Then in last stage, the technology becomes stable, usable and widely adopted. It's no longer hyped, but it is practically used. Then the next point is the cycle indicates the time needed for mainstream adoption. See, hollow circles represents the technology will become widely used in about 2 years. Then gray cycles represents the technology will be common in 2 to 5 years. Then solid circle represents it will take 5 to 10 years before it's commonly used. Triangles represents it will take over 10 years to fully mature and be widely adopted. Crossed circles represents the technology will become outdated before it even becomes useful. Moving to the next point, see examples from 2010 hype cycle. The first is cloud technology, expected to take 2 to 5 or more years to reach productivity. Means cloud computing was getting popular but not yet fully established. It was expected to become a mainstream within 2 to 5 years. Then 3D printing, 5 to 10 years for mainstream adoption. 3D printing technology was still developing and needed 5 to 10 years to become widely used. The next is mesh network sensors, more than 10 years. The next is mesh network sensors, more than 10 years. Means these sensors were still in the early stages and needed a decade or more to become common. Next is broadband over a power line. That is, this technology never became practical and was expected to disappear before it became useful. Yes, next is promising technologies. These were technologies that seemed promising and innovative in 2010. The first one is clouds, using a remote servers for computing and storage. Then biometric authentication, using a fingerprints or a facial recognition for security. Interactive TV, making TV more interactive with on-demand content. The next is speech recognition, allowing computers to understand and respond to voice commands. Then predictive analytics, using data to make predictions about the future trends. Then last one is media tablets, devices like iPads that were becoming more popular. Thanks for watching. We'll continue in the next video.